So independent, if you're looking at playing cards and someone asked you, what's the probability of drawing two kings? What would you say? Turn to your neighbor and tell him, what's the probability of drawing two kings? So a question came up when I say the probability of two kings. I went in, I drawed. I didn't say that. I didn't record that, did I? Anyway, I drew one king. That's 4 out of 52, right? If I didn't replace it, now how many kings are left? 3 out of 51. So it would be you do one, then you do the next. See how easy probability is? You do one, then the next you multiply. Okay, no problem with that probability. 4 out of 52 times 3 out of 51. Now, independent means that you put it back each time. It means that because I drew a king the first time, it's not going to influence the next time, because when I put it back, it's still 4 out of 52 times 4 out of 52. So independent means the first one doesn't influence the second one. And I just like to think of it this way. You put it back. Now, mathematically, what that means is that you don't have any weird conditions. So all you have to do with the intersection calculation is take the probability of the first times the probability of the second. In other words, the probability of drawing the first king was 4 out of 52. Probability of the second king was 4 out of 52. Yeah. So what's interesting is when you look at the conditional part, the conditional part is the probability of the intersection. If they're independent, the probability of A times the probability of B is the intersection. And when you divide by the probability of B, what cancels out? Probability of B. So that's going to give you the probability of A. So it's almost like you don't need to worry about that other situation. All you have to do is worry about the first one. So when you hear the word or see the word independent, mathematically, this is what I want you to think about. It's the intersection is the product of the two. That's going to help a lot. All right, let's do a quick little question about it. In 1984, United States, proportion of all births that were cesarean section deliveries is 15 out of 100. Okay, that's a lot. 15 out of 100. Anybody want to share how many of you were cesarean births? A few in here? Great. Is it fun or? Don't know. Okay. All right. When cesarean deliveries are done, 96 out of 100 babies survive. So that's very good. What's the probability that you randomly select a baby that's born that they were surviving from a cesarean? So in other words, 15 out of 100 is the probability of the cesarean. 96 out of 100 is what? It's the surviving knowing that it's cesarean. So it's survival knowing that it's cesarean. So this is a conditional probability. It's going to lead into my next thing here. But 96 out of 100, 15 out of 100. So if we look at the formula that we had, the conditional probability, survival, knowing, and cesarean is going to be the intersection of cesarean and survival over the probability of cesarean. So if you look at this, we can figure out what we're looking for here is the probability that it's a surviving baby and it's a cesarean. Let's use a little logic here. Use a little logic. If it's 15% cesarean and 96% of those are going to be surviving, do you think it's going to be more or less than 15%? Okay, you have 15% of all the babies are cesarean, and of those, 96% survive. Do you think that's going to be more or less than 15? A little less, isn't it? It's going to be somewhere between 14 and 15, wouldn't you think? Okay, so let's see. So this conditional here was 0.96. this is what I'm looking for. The probability of surviving babies intersecting cesarean babies. Over, I think it was 0.15, right? So if we're solving for this, you're going to get 0.96 times 0.15, and what is that? And cesarean. Is this going to be like 0.148 through calculators? I don't have it, but that's what I would guess, around 14%. So that's using conditional to answer a real question. Again, the cesarean babies were 15% of all the babies. Of those, the condition is if they're cesarean, 96% will survive. Then if we want to know the percent of cesareans and surviving babies, it's going to be 14. All right, and then that brings us to Bayes' theorem. Bayes' theorem is kind of a really interesting idea. We're going to take two worlds, the world of A and the world of B. Okay? B has two conditions. It can either be B or it can be not to be. All right? So it's either B or it's not in B. And A is in both worlds. We're not worried about not A. All we're looking at is A. So let's say we wanted to know the probability of A. So here's what we'll do. We want this part right here, this part, which is the intersection, okay, of A and B. What is this part out here? Intersection of A and what? Not B. All right, so we're looking good here. We've got A intersect B, A intersect not B, and the probabilities in the next step. Now, the probability of A knowing B is the probability of A intersect B, which we just said, over the probability of B. And likewise, the probability of A not B is the probability of the intersection of A intersect not B over probability of not B. Okay? If you do a little cross multiplying, you can solve for these two. Okay? And so this here is probability of A knowing B times the probability of B. And the probability of A knowing not B times the probability of not B is going to be replacing the probability of A intersect not B. This is Bayes' theorem. That is completely unhelpful. Okay? You don't get that, do you? How many of you understand it from watching that? I don't. It's just confusing. The formula for Bayes' theorem, when you solve for all of this, is really a logic type problem. And I would like you to think of this. This is Bayes' theorem of two events. You can have two things happening. Let's say you have event A happening or you have event A not happening. Then you have two conditions, the condition here and not here, and the condition here and not here. So it's really two things happening. Three probabilities are usually given. And when we divide it into this, we'll get arms that I'm going to kind of help you with. When you have these arms, you're going to be able to find these probabilities instantly. And so let's take a real example, and I'm going to show you how absolutely easy these are. By the way, this is probably the most helpful probability that you're going to learn in this class. This could save your life, and we'll talk about that tomorrow. That's kind of a good cliffhanger. I feel like one of those 10 o'clock, you know, the world's going to explode, news at 11 or something, but no. All right, so we have two machines. They both produce Beanie Babies. One produces Beanie Babies, an old machine, and it's 40% of all the Beanie Babies are made on this old machine. 3% effective. It's awesome. But this new machine, 60% are made. They make them a lot faster, but there's 5% come out defective. So you have three things that we know about. What machine the Beanie Babies are made out of, and then how each machine is defective. So what we're going to do is we're going to make a little diagram here. 0.4 is for machine A, 0.6 goes to machine B, and to be defective in machine A is going to be 0.03. How about being effective, not defective, is going to be 0.97, right? And then if we go down to machine B, we're going to have what percent is defective? 0.05, and this will be 0.95. So here's the question. An item is selected at random. What's the probability that it's defective? So here's how I like to do it, and I hope you're not closing up shop here. This is really important. If it's defective, it's going to be this arm, and it's going to be this arm here. These are the two arms that you're going to multiply to get defective. Probability of defective. You have the 0.4 times 0.03, or you have the 0.6 times what? 0.05. So now we get to this part. An item is selected is defective. So you know the thing is defective. You want to know the probability that it comes from machine B, knowing that it's defective. Okay? So let's look at defective. These are the possible defectives. 0.4 times 0.03 plus 0.6 times 0.05. And then the fact that it's the B defective, is it A, B, C, or D arm? The B is defective. C. So it's going to be 0.6 times 0.05. And so all you do is you go 0.6 times 0.05. That's the probability of a defective in B over all the possibilities of being defective, which we just take arm C and arm A. And then you multiply it out and you got it. That's Bayes' theorem.